This is Physical Chemistry, Part 2, Chemical Kinetics, Chapter 36, Complex Reaction Mechanisms, Section 36.1, Reaction Mechanisms and Rate Laws. A reaction mechanism is a collection of elementary kinetic steps. Let me give you one example here. Two N2O5 molecules react to produce 4 NO2 and 1 molecular oxygen. And this is a complex mechanism. So do not intuitively assume this is a second-order reaction. This is not a second-order reaction. I will prove it to you. It's actually a first-order reaction, despite this coefficient. Again, this is because we should not treat this as an elementary step. This is a mechanism. Let me show you the Lewis structure of N2O5 first. So over here you have this nitrogen forming a double bond with this oxygen, a single bond with this oxygen, the bridging oxygen, and over here this is a so-called a donor-acceptor bond. The nitrogen donates 2 lone pair electrons to form this bond. Again, if you just imagine two such molecules collide with each other, it's very unlikely for this reaction to take place and form 4 NO2 and 1 molecular oxygen simultaneously. The probability is small. What's the chance of just breaking this bond and then breaking this bond and then form a new bond between the two bridging oxygen atoms simultaneously? Again, the chance is small. So what's the more likely mechanism? It's right here. All right. By the way, there's a saying: kinetics is fact, mechanism is fiction. So this is our fiction here. We propose that this mechanism contains these 4 elementary reactions. All right, and then we look at these 4 elementary reactions and count how many chemical species are involved. 1, 2, 3, 4, 5. 5 species are involved. And that means we can write out 5 differential equations, 1 for each species. Again, if you have 5 species, you can write out 5 differential equations, 1 for the description of the change of the concentration of each species. Now let's define the reaction rate. The reaction rate is how fast this reaction proceeds. So it can be defined as the consumption rate of N2O5. It can be defined as the production rate of NO2 or oxygen. To analyze this mechanism, it's probably more convenient to just define the reaction rate to be the consumption rate of N2O5. So it's right here. Again, this is the consumption rate, so this derivative is negative. That's why we put another negative sign in front. And also we have this 1/2 here. This is because for one such reaction to proceed, you need to consume 2 N2O5. For 1 mole of such reaction to proceed, you need to consume 2 moles of N2O5. All right, so that means, well, the change of this N2O5 is twice that of the reaction. Therefore, we need to put this 1/2 here. If you happen to use NO2 to define the reaction rate, you need to have the production rate of NO2 divided by 4. If you use O2, well, then that's fine because the coefficient is just 1 over here. Now let's look at N2O5. Again, we're looking at differential equation here. N2O5 is involved in 2 elementary reactions. This one, well, it's consumed here, and this one is produced in the second step. So in the first step, it's consumed. So we need to have negative K1 times N2O5. So over here, negative K1 N2O5. Where's the negative sign? Well, there's another negative sign here, so negative is positive. N2O5 is produced in the second step. How fast? The rate is K minus 1 times NO2 times NO3. It's right here. All right, again, we need to take this negative sign into account. So now we have the expression of the reaction rate. It's this. However, we do not know how this N2O5 or NO2 or NO3 change with time. Now, how do we tackle this problem? We'll use the steady state approximation for the two very reactive intermediates, NO and NO3. All right, again, you can apply steady state approximation to the very reactive intermediates in any chemical mechanism. So what is the steady state approximation? We're going to assume the change of NO with time is 0. The change of the concentration of NO3 with time is 0. All right? We're not assuming the concentrations of NO and NO3 are 0. No, we cannot do that. We cannot do that. What we do is we assume the change of the concentration of NO with time is 0. That means the first derivative of NO with time is 0. This is the steady state approximation. So now let's write out this steady state approximation. dNO over dt is roughly 0, and also we can expand this dNO over dt in terms of, over here, a fairly complex expression. How did I get this expression? It's very simple. We just need to focus on this NO, right? And look at this 4 elementary steps. We check for NO. We look for NO. NO appeared here. NO appears here. So NO is produced in the third step here. The production rate is K2 times NO3 times NO2 times NO3. So it's right here. And NO is consumed in the fourth elementary step. The rate is K3 times NO times NO3. So it's right here. Now we know this is roughly 0 because the change of NO with time is roughly 0, assuming this steady state approximation. And then we converted this terribly complex differential equation to a much simpler algebraic equation, and we know this NO is proportional to NO2, and the coefficient is K2 over K3. So again, we apply the steady state approximation to the highly reactive intermediates in a chemical mechanism. But how do we know these two are highly reactive? One, you can do some literature search. Two, you can run some quantum mechanical calculations to determine which intermediates are highly reactive. So for now, I'm going to just tell you these two are highly reactive, and you can make steady state approximation. So we got the first equation here. It's going to be useful, and we're going to apply the steady state approximation to NO3 as well. This time, it's a little bit more complicated. Again, you need to look for NO3 in these elementary steps. NO3, 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 NO3. So this NO3 appears in all 4 elementary steps. It's produced in the first step. It's consumed in the second, third, and fourth steps. And therefore, we're going to write out 4 terms, 1 positive term here and 3 negative terms. So by doing so, we again converted this complex differential equation. It's very complex because it contains many variables. NO3, we don't know how this changes with time. And we have time here, we have N2O5 here, and we have NO2 here, and we have NO here. So there's no way for us to solve this differential equation. By using the steady state approximation, however, we can say, well, this guy is roughly 0. So this is roughly 0, and then we are looking at a much simpler algebraic equation. And by the way, K3 times NO is just K2 times NO2. So over here, K3 times NO is just K2 times NO2. Alright, so again, we have these 2 algebraic equations from making the steady state approximations for NO and NO3. We got these two equations, and again this over here, K3 times NO is simply K2 times NO2. So really, these two terms are exactly the same. This term and this term are exactly the same after you replace K3NO with K2NO2. And now we have only three terms. 1, 2, 3. Have three terms. And even better, these two terms, they have a common factor. NO2 times NO3. That's the common factor. So we got this equation. All right. And now we can write out the reaction rate here. It's negative 1/2 times dNO N2O5 over dt, and it's this. We got that from here. Again, this is because N2O5 is consumed in this reaction. It's produced in this reaction. All right, and then you probably can tell that this NO2 times NO3 can be expressed in terms of N2O5. So we just replace this 2 with N2O5. We take care of the coefficients. And finally, we get the reaction rate R, which is a constant, times N2O5. This is a first order reaction. Again, you can of course you can simplify this. This part and this part, they cancel, and this 2 and this 2 cancel. So in the end, again, the reaction rate is a constant times N2O5. It's a first order reaction. And then we define K effective to be this, and then we have a simpler expression here in the end. So again, one more time, this is not a second order reaction. Do not be deceived by the coefficient 2 in front of this N2O5. Well, because this is not an elementary reaction. So if you look at this chemical reaction, again, this is not an elementary reaction. It's a chemical mechanism. It involves 4 elementary steps. All right? And by analyzing these 4 elementary steps, we obtained the expression for the reaction rate. It's K effective times N2O5 to the power of 1. It's a first order reaction. Well, to be more precise, it's a pseudo first order reaction because it's not really a elementary first order reaction. And then we can actually get the expression for N2O5. We set this up. This is the reaction rate. This is the reaction rate, and this is the reaction rate. And then we separate the variables. We have 2 variables, N2O5 and time. We separate them. We integrate both sides. We see this N2O5 changes with time. This is exponential decay. And experimentally, we can also measure how the concentration of N2O5 changes with time. And we will be able to determine this K effective. So we'll be able to determine the value of this K effective, or this K1 times K2, over K minus 1 plus 2K2. Can we determine the values of K1, K2, and K minus 1 separately? Yes, it's possible, but it entails the determination of the concentration of the intermediates. That's a lot more difficult.